SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process. Energetic words can unfold the hidden power of mind. We must be aware about this word to really unravel the power lying within our mind as envisaged by our ancestors. Let us recall what we learnt in the last lecture. In the last lecture, we basically initiated discussion of types of turbopump systems. Several types of turbopump systems have been designed and used by across the globe, but we discuss only three representative one, namely the gas generator, stage combustion and also the expander. Later on we took an example to learn how to analyze a typical turbopump system by considering a gas generator turbopump system. We learned that very small amount of propellant is used for running the pump and also the turbine. And today we will be discussing about the ignition system. And we all know that ignition system or the igniter is very important because of fact that we need to initiate the combustion, particularly for the non-hypergolic propellant system, and we will have to give adequate amount of initial energy such that the combustion can be initiated without any pressure spike. So, therefore, the main function of the igniter is to supply requisite amount of energy to initiate combustion in a very smooth manner in case of liquid propellant rocket engine. And the ignition system will be dependent on the type of propellant, the amount of propellant being burned and also the reignition capability, the space requirements and several other operating parameters as well. So, based on the type of energy use, we can divide the igniter into various types and there are several types of igniters being designed and developed for liquid propellant rocket engines, and we will be discussing only 4 of them. Those are catalytic type igniter or hypergolic ignition system, spark plug and resonance. Let us consider a catalytic igniter, and if you look at catalytic igniter was used in the inception of liquid propellant rocket engine. In case of V2 rocket engine, potassium permanganate was used to ignite the hydrogen for the initiation of the combustion. Nowadays also the catalytic igniter is being used, but with a catalytic bed as I have shown here. And there are various kinds of catalysts are being used. Some of them are platinum, iridium and palladium. This has to be coated with the wash coat and the gas can pass through that, so that it will be ignited itself because of the platinum catalyst and or the any of these catalyst will be there. So, the temperature of the gas will be raised so that ignition can take place. And this is generally I have shown here hydrogen, oxygen and hydrogen case, and it will be started. After that it will be taking over, and this is a very simpler system as it is not having the transformer or any other component which is required. So, therefore, this is being used for a smaller rocket engines, and of course, it cannot really provide the very high temperature gas, and the problem with this, the pressure loss across this catalytic bed will be much higher. So, that is the one of the limitation of this catalytic igniter. And let us consider another one, which is known as the hypergolic ignition system. In this case, the hypergolic cartridge is being used, and whenever this fuel and oxidizer, which are hypergolic in nature, will be come in contact, then the liquid phase combustion will be taking place, raising its temperature such that the it can ignite the other fuel and oxidizer. In this example, let us consider the fuel and liquid oxidizer are not really hypergolic in nature. However, it is having a hypergolic cartridge, which is shown here. This is your hypergolic cartridge, and which will be containing the hypergolic propellants. And there are several varieties one can think of. Generally, the ethyl aluminum, which is being used and which is very good, but problem is that it cannot be used alone because of fact that it will be containing lot of residuals. As a result, that may block the systems, and then one has to suffer due to the pressure losses. That is the reason why around 10 to 15% triethyl aluminum along with rest with the triethyl boron by weight are being used. And in this case, once this will be kept in a cartridge, and then it will be really come in contact with that, and whenever the liquid oxygen will be passing through with certain pressure, so that it will be ruptured, they will come in contact with each other, so that heat will be generated during this liquid phase combustion, and then after that, of course, this will produce the high temperature gas, and then it will be go and mix in the main combustion chamber. This is your main combustion chamber. Beside this, the organometallic hypergols are being used, several others, and keep in mind that generally this liquid oxidizer is being bypassed after this ignition, so that the pressure losses can be minimized. And this is again a very simpler systems without any other components to be taken by that. So, therefore, this is being used, but problem with this that it will be pressure losses will be higher, and this also cannot give a large amount of energy, and that for that you will have to use the bigger cartridge and other things. So, that is why it is a limit, it is used whenever it is used for the low thrust and also the simpler systems. Another one is the spark plug. Of course, all of you might be knowing this spark plug is being used in gasoline engine for initiating the ignition process. It consists of basically electrode. This is your electrode, one electrode, and then it is having the ground electrode. There is a spark gap. This gap is basically the spark gap. This is your spark gap here, and that along across this very high voltage is being supplied, such that the ionization will be occurring between this spark gap and leading to the ignition of the mixtures. Keep in mind that for this you need to have a very high voltage transformer with the capacitance, such that you can provide this energy. Generally 20,000 volts being supplied across this spark gap, and which can produce something around 350 millijoule per spark, and this is a quite a heavy systems, and then also like one has to carry this electronic gas gates and to control that. Generally for any combustion around maybe 150 millijoule per spark is good enough to ignite the mixtures. In order to enhance this its effectiveness, generally a chamber is being given here, so that with this supply of fuel and the oxidizer certain amount, so that it will be burnt very locally without affecting the spray and other things, so that generally this fuel and oxidizer will be in gaseous phase. So that it will be producing the high temperature and pressure gas, such that the larger engine can be ignited very easily. Of course, that is known as basically the spark touch, and this is known as spark touch, where having a chamber in which the fuel and oxidizer will be burnt in a small chamber. So, nowadays the spark touch is being used in rocket engine, particularly large rocket engines, and there is another one which is a very important one and interesting one, that is the resonance type. This is your resonance igniter. In this case, the hydrogen at a high pressure is expanded across a sonic orifice or a nozzle, such that its temperature will be raising. You might be knowing that by Joule's Thomson law, that is the hydrogen when it is expanded will be getting high temperature, and around it can reach around something 1400 Kelvin, and such that this gas in a small chamber, that is we call resonator cavities, the gas will be hydrogen gas temperature will be increasing to 1400. Then when it mixed with the oxygen, then it will be reacting, because it will be igniting itself, and this gas, hot gas with a high pressure also will be coming out like a touch outlet, and this can really help in igniting the main combustion chamber, which is not shown here. So, this is a very simpler systems without any other system like your spark plug, where you need to have a transformer, you need to have a capacitor, you need to have electronic circuits and other things. So, therefore, these are the simpler one, but only thing is that one can use this for liquid oxygen, liquid hydrogen systems, because hydrogen is the gas which can really get this high temperature when it is expanded through a nozzle. How can a proper igniter be selected? As I mentioned earlier, it will be depending on the type of propellant, restart, safety, and also the altitude rewrite capability, weight and space. This is the important criteria for choosing an igniter for liquid propellant rocket engine. So, let us look at now the last topic in this liquid propellant rocket engine, that is the combustion instabilities. So, what do you mean by that? We know that the combustion will be taking place. In this case, the feed line will be having some pressure, and this pressure will be fluctuating due to some reasons, due to the operation of valve, and when it is passing through the valve there will be turbulence, and this pressure fluctuation may lead to some changes in the combustion process, in the combustion chamber, resulting in some change in pressure. But those pressures are really very small and both in magnitude and also the frequency, therefore, it may not be affecting. That means, in normal operation, the pressure fluctuation in the combustion chamber of a liquid propellant rocket engine, due to its complexities, always will be there. It is not as smooth as what we can think of, and but that is not really the combustion instabilities. The combustion instabilities will be occurring only when it will be of a certain frequency range and also the amplitude, and when this will be go beyond this acoustic oscillations, then only it will be detrimental. One has to consider that as a combustion instability. For that, let us look at the variation of chamber pressure with time, and you can see this I have shown here some of the fluctuation, not that all these things will be occurring in the combustion chamber. However, I have just combined various kinds of the pressure oscillations one can get in a combustion chamber of the liquid propellant rocket engine. So, this random fluctuation will be always existing, as just now I was discussing. However, there might be a situation where there will be low frequency oscillation, like this kind of things will be there. And there is another situation where very high frequency oscillation will be there. There might be a situation where there will be a pressure spike, as we were experiencing or we had seen also in case of a solid propellant rocket engines. The combustion instability can occur in solid propellant rocket engine as well. However, there the maybe it is less likely as compared to the liquid propellant rocket engine. And generally, when this pressure versus time being data being taken from a running of a liquid propellant rocket engine, and one can make the FFT of those data, one can get the frequency ranges. So, based on these frequency ranges, we can divide these combustion instabilities into 3 categories: low frequency instability, medium frequency instabilities, and the high frequency instability. Low frequency instability will be occurring when the frequency range is less than 400 Hz. Keep in mind that this is the thumb rule what is being accepted and used by the various designer and researcher. There is nothing sacrosanct about it, and this low frequency instabilities also known as chugging or system instability, because of fact that feed line will be having certain oscillation which may coupling with the combustion or the pressure due to the heat release, and then when it is coupling, then it may lead to the low frequency oscillations, and the sound one can really look at it by this thing and one can say whether it is chugging or not. And the medium frequency instability will be definitely greater than 400 Hertz, and it will be less than 1000 Hertz, so that we call it as a medium frequency instability. This is commonly known as budging or entropy wave. In this case, the oscillation due to flow eddies or the turbulence level and also the combustion can be resonated with the oscillation in the feed system, such that it may lead to a certain frequency or the pressure oscillation leading to combustion instability. And therefore, one can find out how to really separate these things so that one can avoid this. And the frequency is greater than 1000 Hz, we label it as a high frequency instability and HFI, and this is known as the screaming or screeching. And this occurs when there is a coupling between the heat release and the acoustic oscillation in the chamber. So, therefore, this is very dangerous, one has to avoid, and of course, the low frequency instability will be annoying to the ear and other things, so also the medium frequency instability, but this is must be avoided, otherwise what will happen, maybe this pressure oscillation can really damage the rocket engine and it may transfer to the other parts of the rocket engine as well. So, let us look at what we can do to control the combustion instability in liquid propellant rocket engines. Of course, the several methods have been devised by researchers over the years, and we will be discussing some of them, and 3 methods are being used. Those are chemical method, aerodynamic method, and mechanical method. The name indicates that this is quite different from each other. These are, in case of chemical method, the chemical additives are being used to reduce the heat release profile in combustion chamber by factor of 2 or more, such that the instability can be really being dampened out. And this is does not require any change in the hardware, that is the beauty of this system. And there is some other kind of chemical adhesive are being used which can augment the droplet scattering and alter the heat release profile to dampen the pressure oscillation. Keep in mind that you will be playing with the heat release profile, and also you will be playing with to decoupling the things. This is the basic method which are being used in most of the cases. And as I told earlier, it does not call for any change in hardware, and the type of chemical additives depends on the type of propellant being used in liquid propellant, and even also the how it is being used. So, let us look at the aerodynamic method. As the name indicates that one has to change the aerodynamics in the combustion chamber such that one can decouple both the heat release and its profile from the feed line or the any other factors that affect the coupling of both. So, combustion is reduced by changing the aerodynamics in the combustion chamber, and this can be achieved by several means, by using a tangential velocity or tangential flow, or we can use the injector patterns, the angle of the injection, location of the injector, or distribution of drop, such that the distribution of droplet will be changing, because distribution of droplet will be affecting the pressure or the peak pressure. In some cases, if it is a smaller droplets together is there and is pre-mixing, and maybe the group combustion is taking place, that may lead to the higher heat release and such that the pressure oscillation will be higher. And we can also alter the aerodynamics by changing the injection elements, orifice sizes, as I told earlier, the injection velocity and also various other means. So, a change in injector design alters the pattern of the spray and heat release, because the spray pattern will be dictating the heat release, that as we had discussed earlier. By lowering the injection velocity, spray occurs at a longer distance to avoid the pressure oscillations. However, if the injection velocity is very high, then the spray, the smaller droplet size will be formed near the nozzle because of better mixing and the scattering of the droplets, so that it may lead to the oscillations. And by using the higher pressure drop across the injector, leading to a larger droplets, and so that you can leading to the smaller droplets, so that the pre-mixing can occur and then leading to the combustion instabilities. An increase in AC by AT, that is the combustion chamber area and the throat area ratio, decreases the vaporization rate and dampen the combustion instability. Of course, there are several ways of doing that, and that is the reason why higher pressure drop being used across the injectors. And let us look at the mechanical method. Mechanical devices, namely baffles, acoustic dampers, ablative liners, etc., are used to prevent the high frequency instability. And this basically helps in minimizing the coupling between the heat release rate and acoustic oscillations. And let us look at the baffles, and these are basically the baffles which is shown in a planar way, but on the perpendicular to this plane there is a depth which is being used, and this depth of these baffles must be chosen properly such that it can separate the combustion, and then combustion will be not interlinked with each sectors. These are also sectors, right. Sectorial combustion will be taking place, and such that the pressure can be dampened. Generally 15 to 20% of the combustion chamber diameter is used as the depth of the baffle. This is a little design thumb rule which is being used. And let us look at another one, hub spoke type of baffles. It can also separate it into various sectors, like this is your baffles and I mean like this is your hub, and sometimes we call it as a spoke, and it will be having certain depth. So, odd number zones are used to avoid local acoustic zones. So, this is the thumb rule what is being used. So, there might be odd numbers and then such that it cannot be uniform, or the kind of a coupling will be avoided by this. So, these are the methods what has been used, and with this we will stop over, and in the next lecture we will be discussing about basically how to cool a combustion chamber and the nozzle of a rocket engine, both the liquid propellant rocket engines and also solid propellant engine. Thank you very much.